Hello, and welcome to my YouTube channel, Reading Little Blue Books Out Loud. This is a Little Blue Book. It is Little Blue Book number 1748, and it is titled Scientific Crime Detection, written by C. Samuel Campbell. And this is copyright, no date, but all the other ones are in the 20s to 30s. So this is Scientific Crime Detection via 1920s, not the 2000s. So here we go. Let's open her up. Yep, no copyright date. Alrighty, here we go. Scientific crime detection. The application of science to the detection of crime was a tremendous improvement over the crude and inadequate methods of the old school. At the time of the organization of the first police of the world, the Marechaussee of France in 1356, the criminal, if not caught while committing the crime or immediately after its commission, was almost certain to escape apprehension. But today, even 20 years is not too long a lapse of time for the bringing of a criminal to justice. This great advancement, as the great advancements in any field of endeavor, is the result of the application of scientific principles and methods to criminological investigation. No clue is too small for investigation or to escape investigation. When science stands at the elbow of the detective of today, and it is often upon the seemingly trivial that the solution of a crime depends. There is hardly a field of science that isn't, in some form or other, applicable to the investigation of crime. The perfect crime is gradually becoming more and more a myth, for science has shown that the perfect crime was simply a matter of imperfect investigation. What once escaped the criminal investigator has now assumed, under the keen eye of science, proportions more and more alarming for the criminal. What was once a grain of dust almost invisible grows to the size of a boulder under the lens of a microscope. Trickery and fraud. Turning the page. Trickery and fraud, once above detection, now stand naked before the ultraviolet rays. The criminal's fingerprint has become his signature, indisputable and unchangeable. A gun brands its identification mark on the shell, and bullet fire in it, strapped to the ingenious machine that the lie detector. The criminal finds his every attempt to lie charted in black and white. He may even be put in a state where he finds it impossible to lie. Once a man could wash the victim's bloodstains from his clothing and feel safe. Today science smiles grimly and shows him those stains he thought he had removed. Even the world is becoming too small a place for the criminal to hide in. For countries have come to realize the importance of an international identification exchange. Today, a criminal arrested in one country may have his fingerprints shot out to other countries, and his past debts to society, which he thought he had escaped, reach out and demand payment. And these are but a few of the things that happen when science takes up the trail of the lawbreaker. Early in the history of scientific crime detection, the importance of chemistry as an aid became a recognizable fact. Today, woven as it is throughout the whole scheme of modern crime detection methods, it is absolutely indispensable. Again and again, the reader will see it playing its vital role in the investigation of crime of all kinds, ranging from petty theft to the capital crime of murder. So important a part does it play in the detection of the adulteration of foods and drugs that there are chemists whose regular business it is to find evidence of this now very extensive form of crime. It also figures in the determining of the authenticity of disputed documents. When a chemical ink remover is applied to writing, it bleaches the black oxide of iron in the writing to a white oxide. Although it is now invisible, the writing has not been removed. An application of another chemical converts the white oxide into a sulfate, and the writing is restored in a deep yellow. No reference to the value of the application of chemistry to crime detection would be complete if mention were not made of the role it plays in the detection of poisons. Toxicology is probably the field in which the chemist figures most notably in the aiding of the police and the courts of justice. He may be called upon to analyze some suspected food or drink which is present at the scene of the murder. Again, he may be called upon to make a chemical analysis of the stomach contents of a murder victim. Blood tests. There is another field in which chemistry plays an indispensable role. At the murder scene, an investigator is often called upon to determine the identity of a stain which might very possibly be blood. There are several color tests for determining the presence of blood in such stains. In the Guaiac test, an application of tincture of guaiac and ozoned oil of turpentine will produce a blue tint if blood is present. The reagents used in the benzidine test are saturated solutions of benzidine and acetic acid and hydrogen peroxide. 18-year-old stains have been known to give almost immediately the intense Prussian blue reaction of this test. Even boiling does not delay it. In a third test, in which phenolphthalein is used as a reagent, the reactionary color of red can be gotten even if the blood is putrefied or if the object which originally bore the stain has been thoroughly washed. But these are merely preliminary tests, as there are numerous other substances which give a positive reaction. Once the possibility of the presence of blood is determined, however, additional steps are undertaken. Microscopic examination is one of these steps. Under the microscope, the size, shape, and structure of the red corpuscles can be studied. Mammalian red corpuscles, in common with the human being, are round and without nuclei. In fish, reptiles, and birds, they are elliptical and nucleated. If they display the mammalian characteristics, their measurements will come close to establishing their origin, for the diameters vary in thousands of millimeters according to their source. Dried blood, however, usually proves unsatisfactory for this test due to the changes in size and shape which corpuscles undergo through drying and remoistening. In the microchemical test, a further step in the study of blood stains, the dried stain is heated on a microscope slide with glacial acetic acid and a trace of common salt. If the stain contains blood, absolute identification is established by the deposit on cooling of the long, thin, narrow, dark brown hemin crystals, which usually appear X or star-shaped. But as putrefaction or contact with rust may result in a negative reaction, a further test may be required. The microspectroscope test may indicate the presence of absorption bands in the spectrum which are present when the stain contains hemoglobin, the red coloring matter of the blood. The establishing of the human origin of blood stains depends on the Preciptin test. At intervals of several days, human blood serum is injected into a rabbit until 2 fluid ounces have been introduced. The animal is then bled and the blood serum kept in sterile tubes. In this test, a solution of the stain in question is mixed with this sensitized serum, and if the stain has been made by human blood, a cloudy suspension will be produced. No other blood, with the exception of some of the anthropod apes, due to their close relationship to man, will cause this precipitation. If the test were being made to determine the presence of some other animal's blood, then the blood serum of such an animal would have turning the page, would have been injected into the rabbit to produce a serum sensitized to the blood of that particular kind of animal. First, we had the identification of the presence of blood, and later the identification of its human origin. Once it is established that the blood is human, it may become necessary to identify it with a certain individual. This is sometimes possible due to the fact that human blood falls into 4 general groups. The importance of such a test can be seen in a case where a murder suspect may have blood on his clothing, which stains he claims to be his own. If analysis of the blood of both the suspect and the victim indicate that they belong to different groups, the importance of connecting the stain on the suspect's clothing with either the one or the other of these groups becomes immediately apparent. Upon its identification may rest a verdict of the man's innocence or guilt. The microscope. The microscope is probably as indispensable as chemistry in the application of science to the detection of crime. This small instrument in the criminologist's all-seeing eye, for it finds the analyses, these little clues which escape the human eye. Under it, a strand of hair will reveal its peculiarities of structure, which make it possible to trace its human or animal origin. Further, and of significant value, a human hair under the microscope will show growth rings, discovered by E. Carlton Hood, which vary in number in each tenth of a millimeter according to the age of the individual from which the hair has been taken. Also, the examination of the severed end of a hair will tell whether it was broken or cut with a sharp instrument. Dust under the microscope may reveal the most damning information. A man's vocation may be revealed by particles on a strand of his hair. If a suit is placed in a bag and beaten, the dust will disclose a man's occupation, evidences of the places he has frequented for some time, possibly tiny grains of the powder used by his murder victim. If he has drilled a safe, dust particles of the metal will be found in his clothing. Vacuum cleaners have been run over the floor or carpet at the scene of a murder and have gathered particles of soil or grains of sand brought in on the shoes of the criminal. Studying under the microscope, they have, due to their particular characteristics, led the police literally to the doorstep of the murderer. A murder case is useless without a corpse to prove that there has been a murder. Under these conditions, the murder suspect's shoes have often helped the police out. Once a study of the scrapings taken from a suspect's shoes showed the police that he had buried the corpse in a certain swamp. Photography. When one thinks of the role which the camera plays in police science, one is likely to think first of the rogues gallery, or the use of it, which is termed in police circles as mugging. Not only do these front view and profile photographs furnish permanent records for future identification purposes, but they also play an important part in a criminal's apprehension if he has escaped from prison or is wanted for more recent criminal activities. With his picture in the files of the police, it is only a matter of hours until the country or the world, if the case warrants it, is flooded with posters bearing his photograph description and fingerprints. Photographing the scene of a crime gives the police a permanent record of the scene. Little details, which may later assume gigantic importance, are not lost through human inefficiency to note and record them, for nothing escaped the camera lens. In France, the police photograph the scene from every possible angle, realizing that the solution of a crime often depends upon evidence seen only from a certain viewpoint. Enlarged photographs of fingerprints, questioned documents, questioned handwriting, pictures taken through a microscope, murder bullets, and practically any kind of evidence play their part in winning convictions from juries when presented in court in conjunction with expert testimony. That testimony, without the photographs to illustrate how the expert arrived at his conclusion, would often mean that his testimony would be too technical for the jury to grasp. Yet upon the testimony may hinge the entire case. It has also been discovered that the camera may introduce evidence which would otherwise escape the naked eye at the murder scene. The body of the murder victim may possess traces of violence in the form of bruises and other marks resulting from struggle. Yet these marks may be invisible until they they have recorded themselves on the more sensitive photographic plate. The Bertillon system. Despite the fact that the fingerprint system of identification has practically suspended the Bertillon system, a word concerning this earlier method based on the measurements of the bony parts of the body is advisable. The following measurements are taken in the metric system: height, reach, height of trunk, length and width of head, width between cheekbones, length of right ear, length of left foot, length of left middle finger and left little finger, and length of left forearm, the color of the eyes, hair, and complexion, and the description of moles, tattoo marks, scars, and other peculiarities are also included. Fingerprints. Although fingerprints were used by the Chinese about 2000 BC, it is only recently that they have taken their proper place in criminal identification. When a fingerprint is found at the scene of a crime, it is dusted and photographed, or over the dusted print may be poured a solution which forms a thin, transparent film. Turning the page. Okay, which forms a thin, transparent film in a few seconds. When lifted, this film bears a perfect reproduction of the print and may be carried about by the investigator as he would carry about a photographic print. Classification of fingerprints is based on the assignment of a numerical value to them according to their patterns. These patterns are divided into 4 general groups: arches, loops, whorls, and composites. What is termed the outer terminus of a fingerprint is the delta, or small triangular area in the pattern. The inner terminus is the core, or the point in the center of the design. Arches are designs in which ridges cross the finger without recurving and usually are without deltas. If the ridges thrust upward in the center, tent fashion, it is called a tented arch. Recurving lines and no delta, or a delta and no recurving line, indicates an exceptional arch. A loop is a pattern in which the ridges start at one side of the design, approach the upper corner of the opposite side, and then return to their original side. Here there is always one delta. If the downward slant of the ridges above the core or inner terminus is toward the little finger, it is an ulnar loop. No, ulnar, U-L-N-A-R, ulnar loop. If toward the thumb, regardless of hand, it is a radial loop. If loop patterns, the ridges, in loop patterns, the ridges are counted between the inner terminus and the outer terminus, between the core and the delta. Whorls are those patterns where within the ridges make a complete turn, forming ovals and spirals. In these patterns, there are always 2 deltas. If the lower ridge of the left delta is traced to the right delta and is found to meet or go inside or outside it with not more than 2 ridges intervening, the print is a meeting whorl. If it goes inside the right delta with more than 2 ridges intervening, it is an inside whorl. It is an outside whorl if it goes outside the right delta with more than 2 ridges intervening. Composites are combinations of other patterns and have 2 or more deltas. The print is a central pocket loop if 1 or 2 of the ridges of a normal loop form a whorl in the center. Normal loops which bend at an angle to form a small pocket at one side are called internal pocket loops. Twinned loops are patterns in which there are two loops. Those patterns too complicated for other classifications are termed accidentals. The identification value of full fingerprints is fairly well known amongst the laymen, but that identifying may be established from a tiny fragment of the ridge formation of a print is not so well realized. The fragment is enlarged many diameters, and the size and shape of the individual sweat pores, which are invisible to the naked eye, and the number of the pores to a given length of ridge formation are compared with the fingerprint of the suspect. If there is a corresponding bit of print, positive identification has been established. And I think we'll stop there for the first part of book number 1748, Scientific Crime Detection, written by C. Samuel Campbell. And we'll see you for part 2.